random sky, and then they put in it what's called the power spectrum. Well, you see, one of the most impressive pieces of evidence for a lot of the ideas that show into the early universe is what's called the lambda-co-dot matter model. You can predict. What you do is take the whole sky, and then you kind of analyze it in terms of different harmonics. So you imagine, you might think it's a bit inappropriate for the sky, but if it was a balloon or something, you see how it vibrates, what different frequencies might it vibrate. And then you analyze the whole sky in terms of those harmonics, called the power spectrum. And you have this curve, which has all sorts of wiggles on it, and the theory predicts this curve to great precision. So you can see it follows the curve very, very closely. So what people tend to do is say, well, you should put that in if you want to have a really good simulation, which looks like a plausible sky. But then there are a lot of parameters left, and you can turn them around and make them completely random. And then they say, well, look, you still get these bits, they're not that unlikely. Well, my colleague does it and says, no, no, that's all wrong, because if you're putting in the real sky, if these things are really there, you'll see them in the simulation. And they say, no, no, we haven't taken the real sky. We've taken all these free parameters and turned them around, and you still see these things. And he says, well, there's something very recent I'm going to tell you, which is just last week, because I'm being email contacted with my colleague here. And the suggestion is the following. Don't take the real sky, and I'm afraid I should have drawn me one of these graphs, because they fit the predictions of the theory and the curves fit very closely. Until you get way down where you're analyzing very, very high frequencies of your drum, if you like. You're looking at little tiny wiggles, not just the main L values. L values are very, very high, so very, very little wiggles on the drum. And what you find is that, okay, we don't fit down there, but then you wouldn't expect it to because there are lots of errors and so on. So what I'm suggesting is to say, okay, take the simulated data, that is to take the data, not the real data, but take the data that the theory gives you, the lambda CDM co-dot matter theory gives you, which fits the curve very well, but down here, it does other things. And you put that in, and then you don't see these things at all. These things now become as unlikely as we thought they would. Now, I guess the experts will perhaps know what I'm talking about, but it's a little bit technical there. The point is, it does seem, and I think I'm prepared to say this now, that these things are real. That they really are events which can be explained by these explosions. Not saying necessarily they are these things, but they can be explained in this way. They are in fact predicted, because the theory says they should have been there, and they're not there in the current theory. So that's what I'm saying. Now, I think I don't know whether I've got time to give any equations, or should I stop at this point?
It's almost time, but you have a little bit to go.
Okay, well I'll just give you a flavour of what the equations are like. I think I'll just do that, because I can't very well say very much. But I think I promised. Did I promise? I can't remember whether I did it's really what happens as you cross over from one to the other. I want to show that there's some real mathematics here. See, what you would do is you have, I'm not saying anything different from Einstein. It's pure Einstein general relativity. Except we have to extend it to cover the crossover. So what I'm going to do is I have a metric, this metric with a hat on it. The mnemonic is that you have, look at the light cone on the crossover, and where it's got this way, that's the hat, you see. And when it's pointing that way, that's the what checks and effects. I don't know the real name for it. The reverse hat metric. And this is, if you like, us up here, that's the previous eon down there. And this is the metric that we would use, or Einstein would be using. This would be the Einstein in the previous eon would be using that one. And now here we have another metric, which is the bandage, which covers the crossover. So I have a bandage running across here. And this third metric, since that's the one we usually calculate with, is the G without any hat. And each of these is conformally related to the other. So I've got the conformally. There's a capital omega which relates the G hat to the G, And the little omega, see this is a big omega because this omega becomes infinite, as you go up here. You're squashing the metric down by an infinite factor. And here we have a little omega which goes down to 0, which means you're stretching the Big Bang up to a regular metric. And here we have these. And I'm going to, here are the Einstein equations, they hold on both sides. And this curly C is the crossover surface. And here we have, I'm going to suppose, as a convenience, that the rest mass has all disappeared by here. It may be you would have to find a way of having a fall here. But let's suppose its rest mass is actually 0 down here. So that means that the trace of the energy momentum tensor is 0 on this side, which means that the scalar curvature is 4 times lambda, which is the cosmological constant. I'm scaling things so the cosmological constant is the same in all three metrics. You can fiddle around with that to change it, but that's basically a convention. And here we have the energy momentum tensor of the matter, the trace-free matter on the two sides, becoming something smooth right across the middle. Now here we're having the Einstein equations on the two sides, and this is a reciprocal hypothesis, which is that the little omega is minus the inverse of the capital omega. What's the minus sign for? I want to keep things positive on both sides. The little omega goes sailing down to 0 quite happily, and it will become negative prior to the Big Bang, and so to keep them positive on both sides of the minus sign. What we find is, however, that you can't keep the rest mass 0 on the post-Big Bang side. That's the, I'm calling the energy momentum tensor U here because there are extra parts. This is massive material. There's some extra stuff in here. Now, so where does this come from? Well, in the pre-Big Bang place first, the Einstein's equations in the G metric need to be understood. Well, you see, you need to know what the conformal factor is in order to write them down. Well, I'm going to consider this equation here, down here, which I'm calling the permanent, I don't know what you call this thing, it's a pi with a twiddle on the top. Cambridge people call it copenhagen, so I'm happy to call it copenhagen. It's not really known, it's a pi, but anyway, it looks like it. Something with a twiddle on it. So that's, I'm calling this in the copenhagen equation, because that's what is satisfied by a capital omega when the cosmological constant is kept constant on the band. So as you go from the pre-Big Bang to the bandage, the cosmological constant is kept constant. Now this equation has some interest in its own right. It's a conformal invariant equation, which I've written with another omega there, and this operator goes to itself, and here we have the energy momentum tensor of this field, which I'm calling the Fourier field, if you like. And what you find is that Einstein's equations, it's quite an interesting equation here, that the Einstein equations on the bandage are that the energy momentum tensor of the material is equal to the energy momentum tensor of the thing I'm calling the phantom field, which is the capital omega. And that's the thing which tells you how to scale back to the Einstein metric. And the idea is that that satisfies this equation here. Now, the reciprocal hypothesis tells us that we can reinterpret this omega equation on the other side as a real field. So this phantom field, which isn't really giving any degrees of freedom, there's nothing new there, becomes on the other side a real field. And I'm supposing that it's perhaps the initial form of dark matter on the other side. Here we have an equation for what the material is on the other side. I think I'll just leave you basically, this equation tells you what the trace of the energy momentum tensor is. It isn't 0, where this pi thing is a crucial object that I think I thought of when I was last in Copenhagen, but I couldn't quite see what to do with it. But what we do with it, you see, this capital pi, which you see over there, is d omega over omega squared minus 1, which is d of little omega over 1 minus omega squared. And it doesn't matter whether this thing becomes infinite, whether omega becomes infinite, because of the reciprocal hypothesis, it's equal to the little omega. And so it smoothly continues across from one side to the other. So the pi is a nice way of keeping track of what the metric would have done if you had it from one side to the other. It's a finite thing, and that finite object has the property, well, you need a condition on it, which makes your propagation unique, and this condition is that the norm of this thing is a third order in omega. I think I just throw that at you here. I'm not explaining it very well, so I need more time to do it. Let me just say one thing, though, that it's very convenient. See, in physics, at the sort of fundamental level, one often makes what are called Planck units, where your speed of light is pretty equal to 1, Planck's constant is pretty, Planck's constant over 2 pi, that's the Dirac reduced Planck's constant, is pretty equal to 1, and the gravitational constant is pretty equal to 1. For this scheme, it's much nicer if you put the cosmological constant equal to, well, 3, actually. So the cosmological constant is 3 in the units that I'm choosing. And what it means, you can see it from this formula, the cosmological constant is 3. The norm of this pi thing is 1. It's a unit vector. And so what I want to say, it's a unit vector to third order in little omega. And this fixes everything you need. So the evolution, as you go through the crossover, is then completely fixed. I'm afraid I've sort of thrown this at you, rather, at the end. I just really want to show that there are equations which enable you to carry across from one eon to the next, and you can look at these things in detail. They are described in my book back at the time, in the appendix. The complicated equations are all relegated to the appendix. But this, yeah, let me just say, well, you can read that if you like. And the idea is that the tandem field becomes a source of new material on the other side, but the equation that I've got down here forces it completely uniquely what it does. So there's no proving in the evolution except what the equation governs the evolution from one side in a unique way. I think I better leave that with you at the moment. There are lots of things to say which I really can't fit into whatever time of time I try to fit this into. Thank you very much.